Hi everybody. So this is going to be the third pre-lecture video in PCS 622, and so far we've been talking about the Fourier series and how to calculate the Fourier coefficients, and hopefully by now you have some idea that what the Fourier series means. You're adding up these waves. Each wave has a different frequency and a different amplitude. And the amplitude are those Fourier coefficients an and bn. So what we've done so far is actually a little bit restrictive. If I go here, you should be able to see these are the formulas that we've given for the Fourier series. There's the Fourier series here, and those were the formulas for the coefficients an and bn. And remember, this is only applicable to functions which are periodic with a period of 2 pi. So that seems a little bit restrictive. In fact, it's quite restrictive. So what I want to do in this pre-lecture is start to relax that. We want to talk about what we can do to go beyond functions which are just have a period of 2 pi. So we'll do two things. The first thing is we'll talk about what if it has a different period, which is not 2 pi but something else. That's fairly straightforward. And then the second thing is a little less straightforward, which is we can discuss functions which have a finite domain. So if it's only a function which is only defined from 0 up to some other point, which I'm going to call L, if we have a function on that finite domain, we can talk about how we might develop a Fourier series for it. So let's dive into it. Okay, so let's address those two issues. How can we generalize our Fourier series in these two ways? So the first thing, let's assume the function is still periodic, but it has a period which is not equal to 2 pi. Okay, that at least buys us a lot more. We can talk about functions with any period. So we're going to address, let's assume the function has a period not equal to 2 pi. F of x has a period not equal to 2 pi, but we're going to call it 2L. Okay, so L is an arbitrary number. L can be anything. So the period is not 2 pi, but could be any arbitrary value. Now be very careful. It's very common that students miss this, that the period is 2L. Okay, so there's this factor of 2 which confuses people. It's very easy to miss that factor of 2, but in this course our convention is always going to be the period is 2L. Right, so L is the period divided by 2. L is half the period. All right, so it's a periodic function, so that means it's going to be, you can sum it up with, you can create it by summing up sines and cosines of the proper frequency. So it's hopefully obvious. Maybe obvious is a bit strong, but it's hopefully clear that I'm just going to add up sines and cosines, but the sines and the cosines themselves will have different periods. That I need to use sines and cosines with different periods than I used before. Okay, so let's think about what kind of functions I might need to use. So the function is periodic and the period is 2L. So let me draw here. This will be L and this will be 2L. And this will be minus L and this will be minus 2L. So I need to draw a function which is periodic and it has a period of 2L, and it needs to be made up of sines and cosines. So what kind of sines and cosines should I use? Well, hopefully it's not too hard to see that I should use the lowest one, the n equals 1 term, should be the one which has a period of 2L. So it should go kind of like, let me see if I can draw it properly. It should go like this and then come back there, right? So this would be the lowest one. This is the sine wave, which has a period of 2L, and that will be n equals to 1. And then we'll have, I have to add up the higher n's. So my other values of n, or my other functions that I might need to use, would be something like this. So let me draw one more and you kind of get the idea. Let's do the same thing. Put here L and 2L. So n equals to 2 would be something which has a period of L. So n equals to 2 would be something like this, maybe. Let's see if I can do it. So that would be an example of a sine wave which has period of L. And then one more time, something like that. Okay. So this has a period of L, and that would be n equals to 2. And then, of course, I would have to add up all the other ones, but I'm just drawing those two to give you an idea. Okay, so knowing that our function has a period of 2L, and the lowest sine wave that I could write, which has period of 2L, is the one in blue, and then the second one would have half that period, which would have period equal to L, and that would be n equals to 2, and so on. So hopefully you see that these are just rescaled versions of the sine waves that we had been using before, which had period pi, 2 pi, and so on. So just based on that, can you guess, so that's what this clicker question is about, which of these would be a good set of basis functions to use for my Fourier series if the function f of x, which I'm writing the Fourier series for, has period of 2L? You should pause the video and see if you can decide which one of those would be the best choice for the set of basis functions that I would use to describe this this function which has period of 2L. So hopefully you've made your guess about which one of these is the function we need, or the set of functions that we need. It's probably not too hard to see that in general, for n equals 1, the period is 2L. For n equals 2, the period is L. So hopefully it's not too hard to see that in general, the period of the nth wave that I'm going to use needs to be 2L divided by n. Okay. Now we're trying to write down sine of something times x, and I want the period of that to be 2L over n. So sometimes we call this thing k. Let's call it kn. And remember that the thing in front of the x has a period, or is related to the period as follows. So kn is 2 pi divided by the period. And so now let's just substitute in 2 pi divided by 2L over n. That's n pi over L. So now we know the set of basis functions I need to use. It's the one which has n pi over L in front of the x. So the correct answer to this question, which maybe you got it right, is, so the correct answer to this question is B, sine n pi x over L. The thing in front of the x has to match this k up here. And then the period of that, so the period is equal to 2L divided by n. Of course, we also have the cosine, so I'm just using the sine as an example, but we also have cosines, but the cosines will also have the same form, n pi x over L. So now we know that the Fourier series for a function with a period of 2L will look something like this. F of x is equal to, there will be some constant term, which we're still going to call a0 over 2, plus the sum from n equals to 1 to infinity, and we'll still call these an. And then I will have here cosine n pi x over L plus bn sine of n pi x over L. Like this. Okay. So far so good. And you can check that this reduces to the previous case, the special case we've been dealing with so far. You can recover the 2 pi periodic function by setting L equal to pi. Okay, but now L can be anything, and so we have a more general formula here. How do I get the coefficients? What's the formulas for AN and BN? So let's think about that. So my series now looks slightly different because I have this this pi over L sitting in there, and this pi over L sitting in here. But otherwise, it has the same structure. Now, how about the formulas for the coefficients? Do those look pretty similar? The answer is yes, but there are some small differences. Okay, so what I'm going to do a little bit of a trick here, and that is I'm going to, rather than kind of rederive those coefficients, this function that I wrote there is true for any value of x. So I'm going to put in a particular value of x. Let me call define y is equal to pi x over L. I'm just defining a function y is pi x over L. So then x is going to be Ly over pi. So let me plug in above x equals to Ly over pi everywhere. Above. Okay, so I'm just playing around with the variables. What I have is f of Ly over pi is equal to a0 over 2 plus sum over n, 1 to infinity, an cosine of, now x is Ly over pi, so n pi over L times Ly over pi. And you can see the pi's cancel and the L's cancel, so that's just ny. And the same thing happens here, bn sine of ny. So let me just clean this up. Everything cancels except for the y, ny. Now this thing on the right-hand side, this is my usual Fourier series for something which is 2 pi periodic. This is the usual Fourier series when the period is 2 pi. And we know how to get those coefficients. To get the nth coefficient, I multiply the function on the left by, cosine of my and integrate. So now I'll just use the things that we already know. We already know how to calculate these coefficients. An is, I take the function on the left, I take it from minus pi to pi, 1 over pi, f of Ly over pi, cosine of ny dy. And bn, same thing with a sine, right? It's like that, okay. So that's okay, and now to finish the calculation, I'm going to change the variables back, right? So let me now change the variables back to x. So I'm going to make a substitution here. X is equal to Ly over pi, and dx will be equal to L over pi dy. And I'm also going to have to change the limits when y is equal to pi, x is equal to L, right? And when y is equal to minus pi, x is equal to minus L. So this first integral, maybe I'll just do it for one of them. The first integral is going to be like this, an 1 over pi, changing the limits now, right? So the limits now go from when y was equal to pi, x is going to be integrated from minus L to L. F of Ly over pi, that's just x. Okay. Cosine, now y again is pi x over L, so I'm going to have here n pi x over L. And then for dy, I've got dx times pi over L, just like that. And you can see something nice happens here, that this pi cancels with that pi. And it all looks fairly straightforward here. I have 1 over L, integral minus L to L, f of x, cosine n pi x over L dx. And it goes through exactly the same way for the bn term, so maybe I'll just write that one out just to save some time. So there you have it. We have now a Fourier series for a function with period 2L, and we have also formulas for the coefficients, which you can find very similarly to that we've done before, but just have a few extra factors around. You know, notice that the integral goes from minus L to L, so the integral goes over one whole period. The thing out in front is 1 over L, and then the argument of the sine function is different than before. So let me summarize everything together here. So there we have it. Now we have a Fourier series for a function with any period. So it's periodic, but I don't care what the period is. It's a period, and our convention is the period is going to be called 2L. So on this interval minus L less than x less than or equal to L. There's my Fourier series. Looks the same as before, except the arguments of the sine and the cosine are different. And I have these formulas for the coefficients now. Look the same as before, but the limits of integration go from minus L to L. I've got a factor of 1 over L out in front, and the arguments of the cosine and the sine are different. So really, you can just use this one from now on. You notice you recover the old formula in the limit, or not in the limit, but the old formulas are recovered by taking L equal to pi, because previously we discussed period 2 pi. Okay, so there's the first example. We've now generalized to any period. And now let's go on to the second generalization, which is that what if my function has a finite domain from 0 up to something else? It's not defined everywhere. Can we still use the Fourier series for that? So let's move on to the second generalization now, which is a Fourier series for a function on a finite domain. And I'm going to call it 0 less than or equal to x less than or equal to L. Now be careful, that L is a different L, so I wrote it differently on purpose. That small l is not necessarily going to mean the same thing as the capital L, so and I'll explain what I mean by that in a minute. So for example, let's imagine you have a function which is just defined just on a finite interval. So for example, I've got a function that looks like this. Let's pick something like, let's pick something like, that looks like this. And this will be L, the curly L. And this is f of x. So it has some form, but it's only defined on 0 between x equals to 0 and x equals to L. So can you get a Fourier series for this? So can you create a Fourier series for this? Well, no. Actually, no. Because it's not periodic, right? I mean, that's kind of obvious. We know that if the Fourier series is made out of sines and cosines, it's not periodic. So, what are you talking about? But we can do something close, and that's, if you think about it, I could try to create a periodic function which matches this function on the range between 0 and L, and is just periodic outside of that range. So the idea you can create a function which is equal to f of x on that domain, 0 less than or equal to x, less than or equal to the small l, and then is periodic outside of it. And then I could do a Fourier series for that function, and it would agree with this function on the range 0 less than x less than l. So the idea is I make up another function which is periodic, which matches this one on that range, and then do the Fourier series for that. This is called an extension, a periodic extension of the function. This is called an extension of f of x. So once we create some other function which is periodic, we can then do the Fourier series for it. Now if you think about it, there's actually more than one way to extend this function, to make a function which matches this and is periodic outside of this range. So let me give you an example of that. So note, there's more than one way to extend the function. And as an example, let me discuss f of x is equal to x plus 3. That's a very easy function to draw. And we know what it looks like. It looks, this is x, this is f of x. Starts at 3 and then goes up like that. And let's say we're doing it on 0 less than or equal to x less than or equal to 5. So this will be the point x equals to 5 there. Let me show you a couple different ways that you can extend that function. Alright, so what I'm showing here are 3 different ways that you can extend that function. Take a look at this first one on the left. That one, pretty obvious, right? It matches, there's the function, the original one, x plus 3 from 0 less than x less than 5. And then all I did is I just repeated that over and over again outside that domain. So this kind of just straight repeating it is what we call the periodic extension. So this is straight up called the periodic extension. And if I called the original function f of x, I'm going to call this one fpe for periodic extension of x. Notice that this one has a period of 5. The period here is exactly the same as the original domain between 0 less than x less than 5. Now take a look at the one on the second one. This is also matches the same function. So this matches the function there between 0 and 5. But look what happens outside of it. It's doing something different, but it's still periodic. how did I come up with this function? What I first did is I took the original function, which was this part, and then I reflected it over the y-axis, and I got this part. So I made an even function out of the original function. And then I repeated that whole thing again everywhere else. Okay? So what this is called an even periodic extension, or just an even extension. So what I first did is I made the function even first, and then I repeated that even part over and over again. So this is the even extension, or the even periodic extension. I will usually write it like EPE, even periodic extension. Notice the period of this function is 10, right? Here's where it starts, here's where it repeats. So the period of this function is twice as long as the original domain. And then I could do the similar thing, except for instead of making it even, I could make it odd. So here, on the rightmost graph, what I did is I took the original function, and then I made an odd function by rotating that whole thing about the origin to give me this piece. Then I repeated that whole thing over and over again to make something which is periodic. Okay? So that's called the odd extension. And that has a period of 10, also twice as large as the original domain, which was 0 to 5. This I'll kind of write it like OPE, odd periodic extension of x. All of those functions have Fourier series because they're periodic, and they all have different Fourier series because there are different functions. But all of those functions will match the original one on this range. So in fact, I have a finite domain. I can write a bunch of different things which are quote-unquote Fourier series for the function, but they're really like, it depends on how I extend it to make it periodic.